So today we're going to look at the last subtopic for heat, which will be the gas law. Okay, gas law. So now before we look at gas law, right, you need to know some characteristics of gas based on kinetic theory of gas. Okay, now in terms of pressure, so what happens is gas molecules always move randomly, so they are moving randomly. So because of that, what happened? The gas molecule will collide with the wall of the container, okay, and then it will rebound. Okay, so it will collide with the wall of the container and rebound. So what happened? There will be change in momentum. Okay, so there will be change in momentum. So because of that, a force is exerted on the wall of the container. Okay, so a force is exerted on the wall of the container, and then the force per unit area is the pressure of the gas. Okay. Force exerted per unit area will be the pressure of gas. Okay. So, so let's say if you have a closed container, so what we can see here is okay, the gas molecules are able to move randomly. So because of that, they will experience collision with the wall of container. Okay. So because of the collision, what happened? They experience change in momentum. Okay, change in momentum happen. So because of that, there will be force. Force will be exerted on the wall of the container. Okay, so there will be force exerted on the wall of the container. So basically, the pressure is the force acting per unit area. Okay, so pressure is the force acting per unit area. Okay, so pressure will be the force acting per unit area. And then in terms of temperature, so average kinetic energy of gas molecules increases with temperature. Okay, and then volume. In terms of volume, gas molecules move freely and fill the entire space of the container. So the volume of the gas is the same as the volume of container. Okay, so volume of gas is actually same as the volume of the container. Okay, now so we look at the first gas law. So we call it as Boyle's law. Okay. Now, Boyle's law says that pressure of gas is inversely proportional to the volume, provided the mass and the temperature is kept constant. Okay, mass and temperature is kept constant. So what you have here, you have a syringe, okay, connected to a Bourdon gauge. So this Bourdon gauge basically is to measure pressure. Okay, so to measure pressure okay, pressure of gas. So this Bourdon gauge will be used to measure pressure. Okay. So the experiment will be something like this. So you have a piston connected to the Bourdon gauge. So what you're going to do is you're going to get a few data on volume and pressure. So let's say you start off with a small volume. Okay, so you record what is your volume and then you get your pressure. And then you make the volume slightly bigger. Okay, and then you increase some more the volume. Okay, so at least have 5 repeated readings. Okay, and then, okay, so let's say these are the readings that you get. Okay, after that, you are supposed to plot a graph of pressure against volume. Okay, so when you plot the graph, what you will see is, you will see that the graph will look like this. Okay, so when you plot, you see that the shape of the graph will be like this. So this is inversely proportional. Okay, so pressure of gas is inversely proportional to volume. Okay, so pressure of gas inversely proportional to volume. Now, let's say if you plot a graph of 1 over pressure against volume, or pressure against, okay, 1 over volume. Okay, either 1 over pressure against volume or volume against pressure against 1 over volume or 1 over pressure against volume. So what happens? You'll get a graph which is a straight line. Okay, so you'll get a graph which is directly proportional. Okay, so this one, if you plot a graph of 1 over pressure against volume or pressure against 1 over volume. But if you plot a graph of pressure against volume, you get inversely proportional. Okay, so inversely proportional. Okay, now now next. Now let's say if you make an extra column. Okay, so you make extra column here. Now this column you find the value of pressure times volume. Okay, P times V, right? So what happens is you will see that all the value inside here will give you almost the same value. Okay, will give you a same value, or we call it constant value. So from here what we get is we get P times V will give you a constant value. Okay, constant value. Meaning if P1 V1 equals to P2 V2. That means your initial pressure times initial volume equals to final pressure times final volume. That means this times this equals to this times this. This times this equals to this times this, and so on. Okay, so that's why we have the formula for Boyle's law. P1 V1 equals to P2 V2. Okay, so P1 V1 equals to P2 V2. So this is the formula for Boyle's law. Okay, so P1 V1 equals to P2 V2. Example, let's say this one. Okay, we put an easier number. Let's say this is 10. Okay, so this is, let's say, 5. Okay, so if this one is 25, here will be 2. So 10 times 5 will give you 50. 25 times 2 also give you 50. Okay, so that means the value of P times V is always constant. Okay, now so if you look at the graph, right? Okay, so few graph you need to know. Okay, P against V is inversely proportional. P against 1 over volume will be directly proportional. But if they ask you to plot a graph of PV against P, you get a straight line. Because why? This value is a constant. Okay, so the value is a constant. Now, other than that, you must be able to explain why when your volume changes, pressure also changes. So we look at what happened when volume decreases. Right? Now, when volume of gas decreases, what happened? So the same number of molecule will exist inside a smaller space now. Okay, so the same number of molecules going to move inside a smaller space. So therefore, what happened? The number of molecules per unit volume. Okay, so the number of molecules. Okay, so number of molecules per unit volume, because your volume has reduced, right? So the number of number of molecules per unit volume will increase lah. So what happened because of this? The rate of collision. Okay, rate collision between the molecules and the wall container increases. It means it's going to hit the container more frequently. Okay, so because of that, force per unit area, which is the pressure lah, also increases. Okay, force per unit area or the pressure will increase. So like this, right? Okay, so what happens when you make the volume smaller? I can see that the molecules are going to hit the container more frequently. Okay, that means the rate of collision increases. That means the force increases, pressure also increases. That means the force exerted on the wall will be more lah. Because why? The rate of collision will be more now. Okay, so this is what happened. Okay, when we decrease the volume. Okay, but when you increase the volume, you see that the rate of collision become lesser. Okay, rate of collision become lesser. Okay, that means your pressure also decreases lah. Okay. Okay, now we look at how to use the formula. Now we look at the paper 3 question. Now, so diagram A shows a student squeezing a balloon filled with air. Diagram B shows a student squeezing the balloon further upwards. The volume of the balloon decreases and it becomes harder lah. Why it becomes harder? Because when your volume decreases, that means your pressure increases. Okay, so now, based on the information observation, state one suitable inference. So inference we can say pressure depends on volume. Okay. Next. So hypothesis, when volume increase, pressure decrease. Okay. So with the use of apparatus such as syringe, rubber tube, and other, right? So you're supposed to design experiment lah. So based on the right. Okay. So your apparatus is all here. Okay. So this one piston, rubber tube, Gordon gauge lah. Okay. So your aim will be to investigate relationship between volume and pressure. So manipulated variable will be volume. Responding variable will be pressure. Constant variable will be the temperature. Okay. So list of apparatus and material, you can refer here all these apparatus and material. Okay, so we go to the procedure, right? Okay, experiment started by pulling the piston to set the volume at, so let's say we put okay, whatever value you want, let's say 2 cm cube. Okay, so reading of Borden gauge or reading of the pressure Okay, so reading of pressure, reading of Borden gauge recorded. So experiment repeated with volume at so say 4 cm cube, 5 cm cube, just say 6 cm cube, 8 cm cube, and 10 cm cube. Okay. Now, so the way you're going to tabulate your data, so the first column here you put pressure. So, sorry, first column will be volume. Sorry. Okay, so volume will be in cm cube, and then your pressure. Now, unit for pressure will be Pascal. Okay, so unit for pressure will be Pascal. So cm cube. Okay. And can write here lah. Okay, 2, 4, 6, 8. Can So the second column leave it blank because we never do the experiment. Okay, so the way you analyze, you must tell what graph you're going to do lah. Okay, so here will be volume. This column will be pressure. Okay. Okay, now what you're going to do is, okay, look at example of calculation question. A mixture of air and petrol vapor is drawn into the cylinder of a car engine when the cylinder volume is 120 lah. So the pressure is then 2 Pascal. The valve closes and the mixture is compressed until the volume becomes 15. So what is the pressure now lah? So just use the formula P1 V1 equals to P2 V2. So your initial pressure is 2. Your initial volume is 120. Okay. So your new pressure don't know. Your new volume is 15. Okay. So that means it's 240 divided by 15. So 16. Okay. Next example of structured question. So okay, diagram shows this experiment. Okay, so they ask you name instrument K. So K is Borden gauge. Now compare the volume of gas, right? So we can see that the volume of gas here is smaller, here is bigger. Okay, so volume of gas diagram 5.1 greater than diagram 5.2. Okay, compare the pressure. Look at this reading. This one is smaller, this one is bigger. Okay, so that means your pressure is the other way around lah. Okay, so diagram 5.2 greater than diagram 5.1. Okay, compare the number of air particles. Okay, now because this one is airtight, so airtight meaning the number of particles will be the same. So same. So based on the relationship between volume of air inside the container with the pressure. So the bigger the volume, the lesser, okay, the pressure. So name the physics law involved, Boyle's law. Okay. Now using your answers, sketch the graph of pressure against volume. So your graph will be inversely proportional. Okay. And then using kinetic method, explain why pressure changes when gas volume changes to mass. So this one you can choose either you want to talk about what happened when volume increase or what happened when volume decrease. So let's say when I say when volume, right? So when volume decrease, okay, rate of collision between the gas molecules and container increase. Okay. Okay, so because of that, pressure increases. Okay. Now, based on the answer, what happened to the kinetic energy of the air in the particle when air is compressed? Give your reason. So when you compress, right? Okay, what happens is, you see, kinetic energy depends on temperature. As long as you don't change the temperature, the kinetic energy will not change. So your answer, no changes. Okay. So reason because temperature temperature is constant. Okay. Okay. Now we look at example of essay question. Now diagram 11.1, 11.2 shows experiment to prove Boyle's law. The slotted weight of mass 200 gram and 500 gram respectively are placed on the piston of the syringe in both diagrams. So the cross-sectional area of the piston in both diagrams is 20 cm cube, 20 cm square. Sorry. The length of the trapped air in diagram 11.1, 11.2 is 10 cm and 1 cm respective, LCM. Sorry. Okay, this is LCM. Okay, LCM. So now state Boyle's law. So when they ask you Boyle's law, you have to follow this. Okay, so say pressure of gas is inversely proportional to volume provided the mass and temperature is kept constant. Okay, so that's answer for one. Okay, next. Using theory kinetic of gas, explain how gas molecule exert pressure. Exert pressure. Okay, exert pressure on the wall of container. So they give you 4 marks. Okay, so what you must say, you must follow this. First say, got gas molecules always move randomly, so you get 1 mark. Okay, so when gas molecule collide with the wall of container, okay, so when gas molecule collide with the wall of container and rebound, so you can add change in momentum. Okay, change in momentum happens. Okay, so change in momentum happens. So because of that, okay, a force is exerted on the wall of the container. So the force per unit area will be the pressure of gas. Okay, so gas move, molecules are always moving randomly. So what happened when they collide? What happened? They will rebound, and then what happened? There'll be change in momentum. Okay, so because of that, a force is exerted. And then force per unit area will be the pressure. Okay, because we know that F equals to M. F equals to MA, right? Okay, so what is A? A is final velocity minus initial velocity divided by time. So when you times what you get mv minus mu over t. Okay, so this you call it as change in momentum. So change in momentum will produce force. Okay, so that's why so what happens when the gas molecule collide, they will change in direction. So there'll be change in momentum. So change in momentum produces force. And then because of that, you get pressure. Formula for pressure is defined as force per unit area. Okay, so pressure is force per unit area. Force acting per unit area. Okay. Okay, next. Calculate the pressure exerted by the slotted weight on the piston. Okay, so this one, basically, right, pressure is force per area. Okay, now, so what is the force? The force will come from this weight. Okay, so the force will come from the weight. Okay, weight of the slotted weight lah. Now, what is the formula for weight? Weight equals to mg. Okay, because weight is a force. So weight is the force. Okay, so the weight of the slotted weight will exert force. Okay, so the force is because of the weight of the slotted weight, which is 200 grams. Okay, so you have to convert to what they call it. Okay, so this one is 200 grams, right? So it's 0.2, change it to kilogram, 0.2, and then the area here they put there. So your gravity, let's say we take 10, or 9.81 lah. So 9.81 or 10. And then the area here will be 20. Okay, 20, So what you get is 0.2 times 9.81 divide with 20. Okay, so you get 0.0981 Newton cm negative 2. So you can't write Pascal because this area down here is centimeter square. It's not meter square. Okay, and then for this force is still Newton. In order to get Pascal, you must make sure the area is in meter square. Then only the unit for pressure will become Pascal or PA. Okay, but in this case, because I'm not changing to meter square, so I'm going to write Newton cm negative 2 lah. Just leave it like that. Okay, now same thing applies. What is the pressure on this side? So pressure on this side will be pressure equals to force over area. So the force will be the weight, which is mg over a lah. Okay, so now what is the weight? So the weight is 0.5. Change it to kilogram times 9.81. Okay, and then divide the same. The area is same. The area is 20. Okay, the area is 20. So 0.5 times 9.81 divided with 20. So you get 0.24 53. Okay, Newton cm negative 2 lah. Okay. Now next what they ask, what is the length of the trap air? Okay, so what is the length of the trap air here? So this one you can use the Boyle's law formula. So P1 V1 equals to P2 V2. Okay, so what will be the pressure? Initial pressure is this one. So 0.0981 times with. Okay, so in this case, right, because the area is same. Okay, so the area is same. Okay, the area, the cross-sectional area is same. So in terms of volume, it depends only on the length. It doesn't depend on the area for this case because the area is constant. So you just take the length, so 10. Okay, because the area is same, so they will cancel off each other. Okay, because same area lah. So the volume is dependent on the length. Okay, equals to, okay, this one the area is sorry, the pressure is 0.25, 0.2453, and then you times with now. Okay, so what you do is take 0.0981 times with 10 divide with 0.2453. Okay, so you get around 4 lah. Okay, so the L will be 4 cm. Okay, so L will be 4 cm. Okay. Okay, next. So diagram 11.3 shows a cycling pumping air into the tire of a bicycle using a bicycle pump. So you're asked to investigate the characteristic of the bicycle pump, that is the size of the handle, material of the piston, thickness of the wall, and the size of the base lah. So you're supposed to choose the best bicycle pump. Explain suitability of each aspect and determine the most suitable bicycle pump lah. Okay. So what we are supposed to talk about, we are supposed to talk about the size of the handle. So the handle got small, got big. So this one you can answer in a table form. Okay. So we have the characteristic. Okay, characteristics. And then here will be the reason. Okay, yeah. Okay, so the first one you need to talk about the size of handle. Okay, so handle. Okay, handle must be big lah. Big or long lah. Long. So reason will be okay, easy to hold lah. Okay, and then okay, now the material of the piston here they put iron, here they put rubber. Okay, now the problem with iron is, okay, let's say this is your pump, so this is your piston, right? Now if the one here made from iron, okay, if you make from iron, you cannot make exactly the same size as this diameter. Why? Then you cannot push because of the friction. Okay, because of the friction lah. Okay, so you can't move. But this one, because rubber is compressible. Okay, rubber is compressible. So even though the rubber is slightly bigger, okay, let's say this is rubber, right? The rubber is slightly bigger, you can push inside the piston, so that can become airtight. Okay, so that means when you put a rubber, it will be airtight. Because if you use what do you call it, iron, you cannot have airtight. It must be slightly smaller. Then only you can push in. Okay, so that means the material of the this one. Okay, material of piston. Put rubber. Reason so that is airtight. Okay. Okay, next we talk about the size of the base. So size of base. Be big. Okay. So reason more stable. Okay, more stable. Then some more one. Oh, thickness of the wall. Okay, so the wall, thickness of the wall. Okay, so the thickness of the wall must be thick. Okay, must be thick. So reason you can say stronger. Okay, doesn't become dent easily. Okay, stronger doesn't become dent easily. Okay, that means tidak mudah kemek lah, doesn't become dent easily. Okay, stronger can. Okay, so after that, what you must do, you must choose lah, which is the best bicycle pump. Okay, so based on this, you have to choose. Okay, so your answer will be K lah. Okay, so then you write K. After you write this, you say, okay, K is most suitable. Okay, because, okay, so you need to tell lah why. Okay, why K is more suitable. What you must do is, you have to repeat back all the characteristics. Okay, okay, repeat back all the characteristics. Okay, all the characteristics. No need to repeat the reason. Okay, no need to repeat the reason. Okay. Now next we look at the second gas law. So we call it Gay-Lussac's law, or they call it sometimes pressure law lah. Okay, so Gay-Lussac's law. Okay, so this law says that, okay, pressure of gas is directly proportional to absolute temperature if volume and mass is constant. Now the meaning of absolute temperature is temperature in Kelvin. Okay, temperature in Kelvin. Okay, so Gay-Lussac's law talks about relationship between pressure and absolute temperature if volume and mass is kept constant. So what you must do is, okay, you prepare a round flask like this. Okay, so then you connect. Okay, so this round flask, there's trap air. Then you connect to bottom gauge lah, and then you put a thermometer. Okay, you have a stirrer here. Okay, water beaker, and then actually you're supposed to put ice. Okay, so put ice so that we can start at lower temperature. Okay, so you're supposed to put ice. Okay, inside the beaker lah. Okay, so must have ice So inside the water you put ice. Okay, so this round flask is empty. It's just air. Okay, trap air inside. So what you're going to do is, you're going to record different set of temperature, okay, and different set of pressure reading. Okay. Okay. Right. So the first column will be temperature. So temperature. In degrees Celsius. The second column will be pressure. In Pascal. So let's say when the temperature is 10 degrees Celsius, because you put ice, right? So record is the pressure 20, 30, 40, and 50 lah. So you record the corresponding pressure reading. Now after doing that, what you're going to see is, when you plot the graph, so when you plot the graph pressure against temperature in degrees Celsius, you see that the graph will be increases linearly. Okay, so the graph will increases linearly. Okay, so the graph will increases linearly. So this one I call it increases linearly, meaning at 0 degrees Celsius there's still pressure. Okay, 0 degrees Celsius there is still pressure. Now next. So when you plot the graph, right? Okay, so pressure against temperature. So you plot the graph, you get something like this. Okay, you get a straight line. So that means there'll be y-intercept lah. Now let's say, right, what happened is, you take your ruler, you make the graph longer. Okay, so make the graph longer, straight line. Call it extrapolate. So when you extrapolate, what happened is, you see that the graph, okay, will cut the x-axis. That means the temperature axis at the value of negative 273. Okay, negative 273. Okay, so that means the graph will cut the x-axis at the value of negative 273. Now this temperature, we call it as absolute zero. Okay, so this temperature we call it as absolute zero. Okay, absolute zero. Okay, so absolute zero. So now why we call it absolute zero? Because during this time, what happened? The pressure of gas is zero. Okay, so there's no pressure of gas. That means during this time, the gas doesn't exert pressure. Why? Because the temperature is too cold for the gas molecule to move. Okay, so that means they don't hit the container, so you get zero pressure at the time. So I call it absolute zero. Okay, now what we're going to do next is, okay, the y-axis of the graph, which is here, right? I'm going to shift to this side. So I'm going to shift the y-axis to this side. Okay, that means the pressure axis, I'm going to shift to the left-hand side. So that the graph is like starting from origin. And then this negative 273, I'm going to change to 0 Kelvin. Okay, 0 Kelvin. So that's why you get the second graph like this. So this one going to become 0 Kelvin, which is equivalent to negative 273 degrees Celsius. Okay, so 0 Kelvin is equivalent to negative 273 degrees Celsius. Okay, so 0 Kelvin equals to negative 273 degrees Celsius. Now, how from this value change to 0 Kelvin, you need to plus 273. Okay, so when you plus 273, you get 0. So that's why if you want to convert temperature from Celsius to Kelvin, you need to plus 273. Okay, you need to plus 273. So let's say, right, if you make another column, okay, you make another column. Now, this column, you find temperature in Kelvin. Okay, temperature in Kelvin. Meaning, let's say if 10 is 10 plus 273. Okay, if 20 means 20 plus 273. If 30, 30 plus 273. Okay, and then if you find the ratio between the pressure and temperature in Kelvin, okay, pressure and temperature in Kelvin, you will see that all the value inside here will give you a same value. Okay, they'll give you a same value. That means they give you a constant value. So that's why you have the formula. Okay, P over T is constant. So that's why I get P1 T1 equals to P2 T2. Okay, P1 T1 equals to P2 T2. That means your initial pressure over initial temperature equals to final pressure over final temperature. Okay, so P1 T1 equals to, okay, P1 T1 equals to P2 T2. Okay, so now other than that, you must be able to explain why when the temperature changes, pressure changes, right? Now see what happens when temperature of gas increases. What happens? Average kinetic energy of the molecule increases. That means the molecule is going to move at higher velocity. Okay, so since the volume doesn't change, what happens? The rate of collision between the gas molecule and the container increases. Okay, so because of that, force per unit area will increase, which is also the pressure of gas. Okay, force per unit area or the pressure of gas will increase. Okay, so that is right. So when you increase, you see what happens when you increase the temperature, right? So the kinetic energy of the gas molecule increases. Okay, that means the molecule is going to hit the container more frequently. Okay, that means the rate of collision increases. Because of that, the force will increase, so pressure also will increase. Okay, so the force exerted, okay, the force exerted on the wall increases, causing the pressure also to increase. Okay, because the volume is kept constant. Okay, the volume is kept constant. Okay. Okay. So now we look at example of paper 3 question. Now before going on a long journey, right? Okay. Now, before going on a long journey, Sharina measured the air pressure in the tire of the car. As shown in figure A, she found that the air pressure of the tire was 190 kilopascal. After the journey, Sharina measured again the air pressure in the tire as shown in figure B. She found that the air pressure in the tire has increased to 235 kilopascal. Sharina also found that the tire became hot after the journey. However, the size of the tire remains same. So this situation talking about temperature and pressure. Okay, after long journey, because of the friction, temperature will increase. So because of that, pressure also will increase. So for inference, you can say pressure, okay, depends on temperature. Okay, so when temperature increase, pressure increase. Okay. Now, with the use of apparatus such as round bottom flask, bottom gauge, other discard experiment. So this one, right? You are using this apparatus. So this apparatus. So okay, aim of the experiment, right? So to investigation between pressure and temperature. So manipulated variable will be temperature. Responding variable with the pressure. Okay. So constant variable will be the volume. Okay, volume. Okay, list of apparatus and materials, so you can refer to this. Okay, don't forget the ice. So there must be ice. Okay, we're going to start at lower temperature, so there must be ice. Okay, so all these are apparatus. Okay, now, so the water in beaker is heated, stirred, and the temperature of, okay, let's say 10 degrees Celsius. So reading of pressure of Borden gauge is recorded. Okay, so experiment repeated with temperature at 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, and 50 degrees Celsius. Okay, so the way you tabulate your data, so the first column here will be temperature. Second column will be pressure. Okay, 10, 20, 20, 40, yeah. So the way you analyze, so you draw a graph. So temperature, in degrees Celsius, pressure in Pascal. Okay. So no need to plot the graph because we did not do the experiment. This one is just a planning, planning of experiment. Okay. So we look at example 14. Ali pumps his car tires at a pressure of 5.4 Pascal on a cold morning, and the temperature is -3. So what will be the pressure in the tires on a hot day with the temperature of 27? So this one you have to use the formula P1, T1 equals to P2, P2 . So your P1 is 5.4. Okay. And then your initial temperature, -3 plus 273. So always remember the temperature must be in Kelvin. Okay, must be in Kelvin. Okay. And then your P2 don't know. And then your new temperature is 27. Again, convert to Kelvin. So plus 273. Okay, so must always convert to Kelvin. Okay, so 5.4. 5.4 divided with negative 3 plus 273 times with 27 plus 273. Okay, so get P2 at 6. Okay, 6 Pascal. Okay. Okay, now we look at example 16. Now, diagram 5.1 shows trapped air in two identical flasks heated with different quantity of heat. Both stoves are turned off after 10 minutes. So, name the physical quantity measured by Bourdon gauge. That means, what is Bourdon gauge measuring? So, the answer will be gas pressure. Okay, or pressure, so can. Now, based on 5.1, 5.2, compare the reading of Bourdon gauge. So, this is more than this. So, this diagram 5.2. The earlier one is diagram 5.1. So, diagram 5.2 greater than diagram 5.1. Okay, and then compare the reading of thermometer. So same, so diagram 5.2 greater than diagram 5.1. Okay, so in between the heat supplied and the temperature. So the greater the heat supplied, okay, the greater the temperature. Okay, so between the pressure of air in the flask and temperature. So same, the greater the temperature, greater pressure. So based on kinetic theory of matter, explain why this happened. So they only give 2 marks. So only 2 points will do. So you can say when temperature increase, okay, the average kinetic energy of molecules increases. Okay. So because of that, the molecules gas molecules, the gas molecules, okay, collide with the wall more frequently. Okay, the gas molecule collide with the wall more frequently. So name the law involved. So this will be sex law. Okay, due to sex law. Okay, can even call it pressure law lah, but usually okay. Now, one more example. Diagram 7 shows a tire of a car that's going to be used to travel from KL to Kuala Terengganu. So after the long journey, what happened to the temperature of the air in the tire? So it will increase. State other physical quantity that will also increase the pressure. Okay. So name the gas law involved. So same lah. Okay. The sex law. Okay. Now, before a long journey, the driver checked the air pressure of his car tire. The pressure was 200 kilopascal at temperature 27. After the journey, the air pressure of the tires found to be increased to 230 kilopascal. So what is the temperature of the air in the tire after the journey? Yeah? So use the formula P1 T1 equals to P2 T2 lah. So your P1 is 200 kilopascal, and then your initial temperature is 27 plus 273. Okay, and then your P2 will be 230 kilopascal. Then you can find your T2 lah. Okay, so what happened? This one bring up, this one goes up, and then the 200 goes down. Okay, cross multiply, 200 goes down. So it will be 230 times 27 plus 273 divided with 200. So you get T2 as 345 Kelvin. Now, if you want to convert to Celsius, 345, you have to minus with 273. So it will be 72 degrees Celsius. Okay. Now next. The tire in diagram 7 is not suitable to be used on the muddy road. Suggest modification to be done based on the characteristic given. So surface of the tire. Okay. So basically, what we want is, because pressure is force per area. Okay. So if you don't want, because when you have high pressure, what happens? Okay, the tire will sink into the mud. Okay, the tire will sink into the mud. So what happened? We must have bigger, okay, cross-sectional area for the tire. So that means the tire must have a bigger cross-sectional area, so that it doesn't sink much into onto the ground. Okay, so surface area of tire must be big. Okay, so less pressure exerted on the ground. Okay, less pressure exerted on the ground. Okay, now the track of the tire. Now the track basically is for grip lah, for grip, so that it won't be slippery. Okay, so what happened? Let's say this is your tire, right? Okay, what you must do is, okay, this one is like the track is not deeper. So in order to get a better grip, you must have a deeper track. Okay, so the track here must be deeper lah. Okay, so the track must be deeper. Okay, so the track must be deeper. Okay, so reason will be better grip, or not slippery also can. Okay, better grip or not slippery. Okay, yeah. Another example, diagram 1 shows the graph of pressure against temperature for a fixed mass of gas at a constant volume. So complete the following sentence by taking right in the box for the correct definition. So temperature basically is degree of hotness. Okay, degree of hotness. And then what happened to the pressure when the temperature decrease? So the answer will be decrease lah. Okay. Name the temperature at point X. So that temperature we call it as absolute zero. Okay. Then what happened to the motion of the gas at point X, right? So it doesn't move. Okay, doesn't move. It does not move. So right. So what happens when we cool down? Okay, you will see that. Okay. So when the temperature decreases, you see that the kinetic energy also will decrease. Okay, kinetic energy will decrease. Okay. So there become time where they become like just vibrating only lah. Okay. So they are not able to move randomly. Okay. So there's no pressure exerted. Okay. Now the last law you need to know is Charles' law. Now Charles' law says that volume of gas directly proportional to absolute temperature again. That means temperature in Kelvin. Okay. When the mass and pressure is kept constant. Okay. Mass and pressure is kept constant. So how to prove the law? Okay. What you must do, you prepare a capillary tube. So there'll be trapped air inside there. So use a concentrated sulfuric acid. Okay. Because it can absorb water vapor inside the air. Okay. So to get a good result, the air here must be dry. Okay. So you need to absorb the water vapor. So that's why they use a concentrated sulfuric acid. Okay, and then you tie to a ruler lah to measure the length later on. Okay, and then you put inside the beaker filled with ice and water, then just heat up. Okay, so how are you going to conduct the experiment? Basically, okay, you have two columns. Okay, the first column will be the temperature in degrees Celsius. The second column will be volume. Okay, okay. Now the volume is represented by the length of trapped air. So the volume is the length of trapped air. Okay, so this one, if you don't want to write the volume, okay, or you can put length also, it's up to you. Okay, so the volume here will be represented by the length. Okay, so you just measure the length to represent the volume. So that means when the temperature is 10, you record the volume 20, 30, 40, and 50 lah. So at different temperature, record the volume, and then what you're going to get is you're going to get a graph like this. Okay, so when you plot the graph, you get a graph which is increases linearly. Okay, so again, when you extrapolate the graph, you see that it will cut the x-axis at the value of negative 273 degrees Celsius. So again, what you're going to do is you're going to shift the y-axis to this side, so that your graph will look something like this. Okay, and then this negative 273, we're going to convert to 0 Kelvin. Okay, so that's why volume is directly proportional to absolute temperature. Okay, so after that, let's say, right, you make another column. Okay, you convert all the temperature in Kelvin. Okay, that means 10 plus 273, 20 plus 273, convert everything to Kelvin. And then when you find the ratio, ratio between V and T, volume and temperature in Kelvin, you get a constant value. Okay, you get a constant value, get the same value. Okay, so that's why you have the formula V1 T1 equals to V2 T2. Okay, so V1 over T1 equals to V2 over T2. Okay, so other than that, we need to explain why when temperature increases, volume increases if the pressure is kept constant. So what happens is when temperature of gas increases, the average kinetic energy also increases. And then the molecules are going to move with higher velocity. So to keep the constant, to keep a constant gas pressure, that means to make the pressure constant, the volume have to increase. Okay, so that the rate of collision is still the same. Okay, so because if the volume doesn't increase, what happens? The molecules is going to hit the container more frequently. So that means the volume need to be increased. Okay, so that the molecules hit the container with the same rate compared to this. Okay, that means even though here, so when the temperature is low, right? So when the temperature is high. So even though the molecule is moving at a slower rate, but the distance from the wall is shorter. This one, even though the molecule is moving faster, but the distance from the wall is further. So the rate of collision will become the same. Okay, rate of collision become the same. Okay, so example on paper 3 question. Diagram A shows a balloon placed tightly over the mouth of the plastic bottle submerged in water at room temperature. Whereas diagram B shows what happened to the bottle placed in the hot water. So based on this one, right? So what happens when temperature increases, volume increases. So this one is talking about volume and temperature. So volume depends on temperature. Okay, so when temperature increases, volume increases. Okay, next. So aim to investigate the relationship between temperature and volume. Okay, so your manipulated variable will be temperature, corresponding will be volume. Your constant variable here will be pressure. Okay, pressure. So constant variable will be pressure. Okay, list of apparatus and materials, so all inside here. Okay, the water is heated set at temperature of, let's say 10 degrees Celsius. So the length of trapped air is measured. Experiment repeated with temperature at 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, and 50 degrees Celsius. Okay. So the way you tabulate your data, so here the first column will be your temperature, and then this one must be volume. Okay. Now, if you want to use a short form, you have to define first. That means in your variables, you must say temperature. Okay. Right, temperature, comma, theta, and then degree Celsius. Okay, that means you already define what is theta. If you don't define, you cannot use the short form. Okay, so you can only use the short form if you have defined. Okay. So the way you analyze your data. Okay, so the way you analyze, so you plot the graph lah. So your graph will be temperature against volume. Okay. Now we look at example of question. A sample of gas has a volume of 120. To what temperature we have to heat it if you want to double to 200? So use the formula V1, P1 goes to V2, V2. So your V1 is 100, and then your T1 will be 20. You need to convert to Kelvin, so plus 273. Okay, and then your V2 200, and then you find your T2 lah. So same thing, this one goes up, this one goes down. Times 2. So you get 586. So if you want to convert to Celsius, you have to minus. So 586 minus 273. Okay, 1 degree Celsius. Okay. Now next, look at example. Now, figure 1 shows a balloon tightly fastened to the open end of a test tube mouth before and after the test tube is heated. Figure 2 shows the air is trapped inside the capillary tube and by a bit of sulfuric acid before and after the capillary tube is heated. Okay, so observe figure 1, figure 2, state one similarity between the volume of air and the balloon in the capillary tube. So what we can observe is the volume increases with temperature. Okay, I can say, okay, volume increases when heated up. Okay, yeah. Compare the mass of air. So because it's airtight, so the mass is same. Okay, so the mass will be same. Huh? That means the mass inside there will be same because it's airtight. Okay, based on answer, comparison relationship between the physical quantity involved. Huh? So higher the temperature, higher the volume, or the bigger the volume. Okay, so this one we call it Charles' law. Then they ask you based on kinetic theory, explain. So it means what happened when your when your volume changes. So you must use this one. Correct. So when the temperature of gas increases, the average kinetic energy of molecule reduces. Okay. And then the molecule move with higher velocity. So to keep the gas pressure constant, the volume of gas must increase. Okay, volume of gas must increase. Okay, so that the rate of collision of gas with the wall remain unchanged. Okay, so this will be the answer. Okay, another example. Now, diagram 6.1, 6.2 shows experiment is carried out to investigate a gas law. The column of air is trapped in the capillary tube and heated for a period of time. So what is meant by heat? So heat is a form of energy. Okay. Then compare the length of trapped air in 6.1, 6.2, compare the temperature. So compare the length, you can see this one is longer than this. Okay. So you can say diagram 6.2 greater than diagram 6.1. Okay. Compare the temperature, same so 6.2 greater than 1. Name the physical quantity represented by the length. So the length of trapped air actually representing the volume. Okay, volume of trapped air. Volume only. Okay, volume of trapped air. Okay, so relationship between the physical quantity, okay, and the temperature. So the higher the temperature, the bigger the volume. So name the physics law involved. So this is Charles' law. Okay. Then diagram sequence shows a graph obtained from the experiment. The temperature theta is when it's extrapolated intersects. So what is the name given to temperature theta? So this temperature we call it as absolute zero. Okay, absolute zero. That means 0 Kelvin. Okay, 0 Kelvin. Okay. So these are some of the example of gas law question. Okay. So that's all for now. We will continue on the next lesson.